Welcome, everyone. I'm Ricardo Camacho, Director of Product Strategy for Embedded and Safety Critical Compliance at Parasoft. Today, I'm excited to talk about engineering safety for AI with ISO Pass 8800. There's been a lot of interest in this topic, and one reason is that there really isn't another standard quite like it. ISO Pass 8800 brings together functional safety, AI governance, and AI engineering into a practical framework for developing and assuring safety critical AI systems. It was developed for automotive, but the principles apply across many safety critical industries. So if you're not in automotive, don't tune out. All right, let's get started. So let me start by setting the context and clarifying what the standard actually covers. ISO Pass 8800 focuses on AI systems used in production road vehicles, so cars, trucks, and similar platforms where AI can have an impact on safety. It addresses risk that can come from the AI itself, limitations in how it's designed, lack of capability, insufficient training data, or even the effects of random hardware failure. And the scope isn't limited to AI physically running inside the vehicle. You also have external AI services that identifies road hazards, accidents, lane closures, or dangerous weather, and can send that information to an automated driving function where the vehicle can use that information to slow down, change lanes, or make another safety related decision. That external AI then becomes part of the whole safety picture. So the key takeaway is that AI safety isn't just about whether you can trust the AI model, it's about whether you can trust the system as a whole. And that means safety has to be engineered across the entire life cycle. And another very important point is that the standard does not claim that AI can ever be made perfectly safe. Its objective is to identify, manage, and reduce AI-related risk to an acceptable level. And how that's done is captured by the standard, which I'll be covering these key points. Also, ISO Pass 8800, it does not replace ISO 26262 or ISO 21448, also known as SOTIF. It works alongside them. As I just mentioned, ISO 26262 and SOTIF are required, and 8800 also references AI standard ISO IEC 22989 for terminology. And terminology is actually pretty important because AI introduces some different ways of thinking about safety. One of the most important distinctions is between the term insufficiency and a failure. With traditional software, maybe there's a coding defect and the software doesn't behave as designed, so we find the defect, we fix it, and verify that fix. Now, with AI, it's kind of different. Imagine a pedestrian detection system operating exactly as designed, but it encounters a situation that wasn't adequately represented in its training data. Maybe unusual lighting or heavy rain, and it doesn't recognize the pedestrian. There's no traditional software bug to find, and that's a fundamental mind shift that needs to happen. With AI, unsafe behavior doesn't necessarily mean something's broken. Sometimes the system simply is not capable of handling a situation it encounters. For example, autonomous vehicles are trained not to cross a solid white line to prevent them from actually going onto oncoming opposite traffic. Well, some tricksters drew white lines around Waymos, preventing them from being able to move. So I don't know if you saw this, but those videos went viral. But this is a scenario that was not thought of in the lab, but encountered out in the field. No software bug, no hardware failure. It's an insufficiency in training. And that's one of the consequences of AI and a core concept in 8800. And I'm going to continue to address those concerns throughout the presentation. So a key point is that before we can engineer AI safety, we need a common language for talking about AI safety, and the term insufficiency is a big one. Oh, and before I forget, 8800 does give you a common reference for abbreviations because you'll see acronyms like ASIL, ODD, SOTIF, and so forth. Now that we've established the terminology, I want to go into a very practical question. What does it actually mean to claim conformity with ISO Pass 8800? And the starting point is straightforward. If you claim conformity, all defined requirements apply by default. But here's where it gets interesting. ISO Pass 8800 allows for deviations. And that's important because AI can't always be verified the same way we verify traditional software. In ISO 26262 Clause 6 for C++ code, you can perform static analysis, unit testing, code coverage, and requirements traceability to reach a very high level of quality. But how do you apply those same techniques required by ISO 26262 for a neural network? You can't. The technology is different. Instead, you need a different verification strategy. You can run thousands or millions of simulations. You test the AI against very large and representative data sets. You measure how frequently it fails or produces an unacceptable result and establish an acceptable threshold based on the safety requirements and risk of the system. So the standard gives you the ability to deviate from ISO 26262. You can tailor how you demonstrate safety, but you have to justify the approach. You have to define the acceptance criteria and provide evidence that the safety objective is still being met. And I'll go into that a little more detail as we go along the presentation. But there's also another important type of deviation, which is justified nonconformity. And this is where you may not be able to fully satisfy a requirement as written, but you can demonstrate that the resulting risk is being adequately controlled in another way. And this is where safeguards and redundancy become really important. As a safeguard example, imagine an AI-based driving component that it decides that the vehicle should travel at 80 miles per hour through a residential neighborhood. You don't want the safety of the vehicle and passengers to depend entirely on the AI making the right decision every single time. So you surround the AI with an independent, deterministic safeguard. You can have the navigation or map data tell the system that the speed limit is 35 miles per hour. The safeguard recognizes that the AI's command is outside the permitted safety boundary and prevent the vehicle from accelerating to 80 miles an hour. Now, the AI can be wrong, but the system doesn't have to let the error become a hazard. And this is a really important concept in AI safety. You're not trying to prove that an AI model will never make a mistake. You are engineering the system so that when the AI does make a mistake or produces an unexpected output, you have mechanisms in place to detect it, contain it, and prevent it from creating an unacceptable safety risk. So 8800 gives us flexibility, but it's control flexibility with accountability. You can deviate, you can use different verification methods, and you can compensate with safeguards or redundancy. But you have to justify those decisions, document them, and provide defensible evidence that safety is still being achieved. Now, I want to start to explain how AI actually fits into the safety engineering process. Again, ISO Pass 8800 does not replace ISO 26262. It builds on it. If your system doesn't contain AI, ISO 26262 applies as it normally would. But once AI becomes part of a safety-related function, the existing safety process has to deviate and be tailored and extended to address the additional characteristics and risks that AI introduces. And that's the top image in the slide from the standard. And that brings us to another important concept. The AI system isn't an item by itself. It's a component within a larger vehicle system, and that component may include software, hardware, data, and one or more AI models. That's important because when we talk about AI safety, it's very easy to focus almost entirely on the model, but the model is only one piece of the system. Then you have a reference architecture. Data may first go through pre-processing, then into the AI model, and then through post-processing before the result is actually used by the rest of the vehicle. So safety has to be considered across the entire pipeline. So let me use that pedestrian detection example. Suppose a camera captures an image of the road. Before that image ever reaches the AI model, software may resize it, normalize it, filter it, or otherwise pre-process the data. The AI model then analyzes that image and determines whether it's a pedestrian. After that, additional software may interpret the model's output and determine whether the vehicle should warn the driver, slow down, or apply the brakes. So if the vehicle fails to recognize a pedestrian, we cannot automatically assume the AI model was the problem. Maybe the input data wasn't processed correctly. Maybe the training data didn't adequately represent that particular situation. Maybe the model has a performance limitation under certain lighting or weather conditions. Or, maybe there's a defect in the conventional software, or maybe there's a hardware fault affecting the sensor or processor. And that's why 8800 distinguishes between different root causes of AI-related errors. There are specification insufficiencies, there are performance limitations, systemic software faults, random faults. And this distinction matters because different causes require different solutions. If the problem is inadequate training, static analysis is not going to fix it. And opposite that, if there's a defect in the C or C++ pre-processing software, adding more training data isn't going to fix that either. So we have to understand where an error came from, how it propagates through the system, and what safety mechanism is appropriate for controlling it. And that's why you have to look beyond the AI model itself. AI safety is about understanding and controlling the entire chain from the data coming in through the AI to the decision and behavior that ultimately comes out. So now that we understand some of the different ways AI can introduce safety risk, the next logical question is, how do we manage AI safety throughout the software development lifecycle? And that's really what AI safety management is about. The standard has three basic objectives: define the AI safety lifecycle, establish the appropriate safety management process, and then plan and carry out the activities needed to support AI safety. But the bigger message is that AI safety isn't a one-time activity. As you can see on the slide, 8800 integrates AI safety activities into the V process model that we're, all really very familiar with from ISO 26262. We will start with requirements, then we design, then we verify and validate, and then we deploy. But now we actually monitor it during operation, and that's a critical focus. For example, drawing the white line around the Waymo issue, or going back to the pedestrian detection, while out in the real world, if the AI's ability to recognize pedestrian drops significantly or at night or during heavy rain, we may need additional data. We may need to retrain the model's behavior, change the model architecture, perhaps maybe refine our requirements or introduce additional safeguards. And then we verify it again. So the development lifecycle doesn't end when the vehicle goes into production, and that's the iterative nature of the AI safety lifecycle. So we continue monitoring performance and looking for new insufficiencies. And when we discover something, that information can be fed back into development. As a side note, some systems have a candidate AI model that is being developed and trained in parallel with the current deployed model, where it is incorporating new data and lessons learned from operating out in the field. Over time, this candidate model may perform better than the version that's currently deployed, which I find interesting. Anyways, instead of thinking about this life cycle as develop, test, release, done, think of it more like develop, verify, deploy, monitor, learn, improve, re-verify, and redeploy. And throughout the entire process, we're producing work products and maintaining traceability. We need to know what changed, why it changed, what data was used, what safety requirements were affected, and how the new model was verified and validated. Also, what limitations were identified and what evidence demonstrates that the new version remains acceptably safe. Because ultimately, every time we make a safety claim, we need evidence to support it. So AI safety doesn't end when the vehicle leaves the factory. It continues throughout the operational life of the system. And every significant change has to bring safety assurance along with it. Now, not in the 8800 standard, but I've been seeing this out there quite a bit. A DevOps Infinity symbol augmented with the AI development cycle. I like it because it's very clear that the life cycle requires the AI model to be designed, trained, and validated. So, anyway, something I wanted to share. All right, let's now address how do we actually demonstrate that an AI-based system is acceptably safe. With traditional software, we can trace requirements to test, we can perform static analysis, we can run unit tests, we can measure code coverage, and we can demonstrate that the software behaves according to its requirements. But AI changes that equation because you can't simply test every possible scenario that an AI system might encounter. The real world is simply too complex, and AI systems have inherent limitations and uncertainties. So 8800 takes a different approach. Instead of trying to prove that the AI will never make a mistake, we build a structured assurance argument that demonstrates why the system can be considered acceptably safe. So, what does that actually mean? Well, at a high level, we make a safety claim. We explain why we believe that claim is valid, and then we provide evidence to support it. For example, we claim that our pedestrian detection system can operate safely. We can't just say our model is 99.9% accurate and consider, the job done. We need to ask 99.9% accurate under what conditions? Did we test during the day, at night, in heavy rain, in an urban environment or rural roads? What about a particularly obscured pedestrian? What about unusual clothing or unexpected behavior? That's where data coverage becomes part of the safety argument. We need evidence that the data sets and scenarios we used are sufficient, that they represent the conditions that the system is expected to encounter. And there's also robustness testing. What happens when the inputs aren't perfect? Maybe the camera is partially obscured. Maybe there's glare from the sun. Maybe a sensor provides incomplete information. We need evidence showing how the AI behaves under those kinds of conditions. But here's a really important point. Our safety argument doesn't have to depend entirely on the AI being right every single time. We have to design safety into the architecture around it. Remember my earlier example where the AI decides the vehicle should travel at 80 miles per hour in a residential area where the speed limit is 35? An independent safeguard can recognize that the AI's command violates an established safety constraint and prevent the vehicle from executing it. We can also use redundancy, fallback logic, monitoring, alerts, or a transition the system into a safer operating mode when the AI's output is uncertain or outside an acceptable boundary. Those mechanisms become part of our assurance argument. So now we're building a much broader body of evidence, and it's a multi-tier level of evidence. We have data coverage, we have robustness testing, we have architectural safeguards and redundancy that help prevent an incorrect AI output from becoming a hazard. And we have monitoring and operational measures that help us detect and respond to problems once the system is deployed. So model accuracy, failure rates, data size, or any other individual number can certainly be useful evidence, but no single metric tells us the entire system is safe. We have to bring quantitative evidence together. So AI safety isn't a single test, it isn't a single number, it's a structured argument built from multiple layers of evidence that together demonstrate why the system can be considered acceptably safe. Let's now move into deriving AI safety requirements. Just like traditional safety engineering, we start with the system level safety requirements and progressively derive more specific requirements for the AI system. Those requirements define what the AI needs to do, the level of performance that's acceptable, the conditions under which is expected to operate, and importantly, what should happen when it can no longer perform safely. Now, this diagram looks kind of complicated, but the basic idea is actually pretty straightforward. We start with what we already know about the system, its functional requirements, the safety requirements that have been allocated to the AI, and the conditions or input space in which we expect the AI to operate. From there, we bring together traditional functional safety requirements, SOTIF requirements, what we already know about the AI's limitations or insufficiencies, and the results of our safety analysis. And there's an important connection here to ISO 21448 or SOTIF. SOTIF addresses situations where a system can become unsafe even though nothing has necessarily failed. For example, an automatic emergency braking system may be operating exactly as designed, but glare from the sun prevents the perception function from correctly recognizing a pedestrian. No broken sensor and no software defect. The system simply has a limitation under a particular condition. That kind of thinking and guidance from SOTIF becomes especially important with AI because we need to understand not only what the AI is supposed to do, but also the conditions under which it may not be capable of doing it safely. All of this information is consolidated and refined into the AI safety requirements. But notice something else that's really important in the diagram. The information doesn't flow in only one direction. At the bottom, we have feedback coming from safety analysis and from functional insufficiencies discovered during actual operation. So as we test the AI and eventually operate it in the real world, we may discover limitations or triggering conditions we didn't originally anticipate. Those discoveries feed back into the process. We may need to add new requirements. We may need to refine requirements and the conditions under which the AI is allowed to operate, or we may need additional safeguards. And that's why you also see the input space being refined. We're not only defining what the AI needs to do, we're also defining and refining the conditions under which we have sufficient evidence that it can do it safely. And all of this needs to remain traceable and supported by evidence. So AI safety requirements aren't static. They're based on what we know about the system, its safety goals, its operating environment, and its known limitations. And as we learn more through analysis, testing, and real world operation, these requirements may need to evolve. Okay, now that you have your AI safety requirements, the next question is, how do we tangibly satisfy them? One of the first things we have to think about is the AI technology itself. Not every type of AI is appropriate for every safety related application. So we need to consider the available technologies and be able to explain and document why we chose, the one we're using. For example, if we're developing an image-based pedestrian detection system, we might choose a CNN or convolutional neural network because CNNs are well suited for extracting spatial features and recognizing patterns in images. But maybe our application needs to analyze a sequence of sensor measurements over time. In that case, we might consider an RNN, a recurrent neural network, because it's designed to work with sequential or time series data. And depending on the application, we might consider other types of AI. The point is that we need to demonstrate that we thought about the choice. Why did we choose this type of AI for this particular safety related function? What alternatives did we consider? What are its strengths? What are its limitations? And why do we believe it's appropriate for the job that we're asking it to do? But this is only part of the story. And as I've stated before, we also design safety into the architecture around the AI. And that's where things like having redundancy systems and even redundant AI models in case of hardware failure. You can also prune and quantize the model to improve performance and freeze the model so its behavior cannot change while out in the field. Also, there's functional separation, which is really important. For example, if the AI uses a camera to determine whether there's a pedestrian in front of the vehicle, do we really want the safety of the entire system to depend on that one model and that one source of information? Probably not. So we might introduce redundancy by using another source of information. It could be another camera, or better yet, how about radar or LiDAR to provide an independent view of what's happening? We can also perform plausibility checks. If the AI says there's nothing in front of the vehicle, but another sensor indicates there's an object directly in the path, that's a disagreement the system needs to reconcile. We need to decide what happens next. Maybe the vehicle reduces speed, maybe it gives control back to the driver, maybe it transitions into a degraded or safer operating mode, or another independent safety function may activate, which is the fallback strategy. We don't want to give AI unrestricted authority over a safety critical action. Functional separation through independent software or hardware can ensure safety boundaries around what the AI is allowed to do. And this brings us back to the understanding that the AI can be wrong, but the system doesn't have to let that error become a hazard. So choosing the AI technology is itself a safety decision, and once we've made that choice, we still need the architecture and safeguards around it to ensure the overall system can operate safely. Now, one of the biggest differences between traditional software development and AI development is the data set used to train, validate, and test the AI. It becomes a safety critical engineering asset. With machine learning, the behavior is heavily influenced by the data used to train, validate, and test the model. So if the data is incomplete, incorrect, biased, or simply doesn't represent the conditions the AI will encounter in the real world, we can end up with an unsafe system. And that's why 8800 introduces the dataset lifecycle. And it's similar to the V model that you're seeing here on this slide. you have to engineer the data set. And that starts by defining data set requirements based on what the AI system needs to accomplish and the conditions under which it needs to operate. Then you design the data set. What data do you need? What scenarios need to be represented? How much of each type of data do you need? And how do you know what's been collected is sufficient? Then you implement the data set. You can acquire real world data, but you can also generate synthetic data. Then you have verification and validation. Did you build the data set according to the requirements you defined? And there's one more thing in this diagram that's really important. The data set lifecycle doesn't end when the AI goes into production. At the top, you can see new data being collected during operation and feeding back into dataset maintenance because real-world operations may expose a condition we didn't adequately represent in the original dataset. And throughout this entire process, we need traceability. We need to understand how the dataset requirements relate back to the AI safety requirements, how the dataset was created, what it contains, what limitations were identified, and what evidence demonstrates that it's now suitable for its intended purpose. So with AI, you don't just engineer the model, you have to engineer the data set behind the model. So now, how do you actually verify and validate the AI system? There are two objectives. First, we need to verify that the AI system satisfies the AI safety requirements that have been allocated to it. And second, once that AI is integrated into the larger system, we need to validate that the overall system can operate safely under the conditions in which it's actually expected to operate. We may test an individual component. We may integrate several components and then test together. And eventually, we need to test the complete AI system as part of the larger vehicle system. So think of this as multiple levels of verification and validation. Does this individual AI component satisfy the safety requirements allocated to it? Do they still behave correctly when they're interacting with each other? And ultimately, does the complete system behave safely in the real operating environment? And that question is interesting because car manufacturers like Ford, Toyota, Honda, and Nissan use fake cities like M-City in Detroit with roads, buildings, roundabouts, traffic lights, and there are actually other cities. Waymo has the Castle in California. There's also K-City in Korea. But this is expensive and time consuming because there are costs in gasoline, tire wear, mileage, maintenance, and the vast number of scenarios that you need to test against. And that's where simulation becomes incredibly powerful. Today, we can create entire virtual driving environments and manipulate the driving conditions to test for the multiple set of scenarios. You can change the weather, you can change the lighting, you can introduce pedestrians, traffic construction, unusual road configurations, sensor disturbances, or dangerous situations that would be difficult or unsafe to reproduce physically. Tools and environments such as Carla, NVIDIA Drive Sim, DSpace, and hardware-in-the-loop simulations can help engineers create and repeatedly test those kinds of scenarios. 8800 also provides an activity diagram on testing workflow of an AI component. But verification and validation isn't simply about getting a pass or fail result. It helps us evaluate risk, improve the model, refine requirements, and add safeguards. You verify and validate to build confidence through multiple levels of testing across representative and challenging conditions until you have sufficient evidence that both the AI and the system around it can satisfy their safety requirements. So when the vehicle is deployed, safety doesn't stop when it leaves the factory, as I've mentioned. Today's connected vehicles give us something we really didn't have in the past: the ability to monitor how systems are performing in the field, collect information about unexpected conditions, and then respond to what we learn. If an AI system begins encountering situations where its performance degrades or its confidence drops, that information can be captured and analyzed. That information can feed back into the development. And once we've demonstrated that the new version satisfies the appropriate safety requirements, we can potentially deploy that improvement back to the vehicle through an over-the-air update. So OTA gives us a very powerful feedback loop: monitor, measure, learn, improve, verify, update. But there's an important safety point here. An OTA update isn't simply about pushing new software to the vehicle. If we're changing something that affects safety, that change has to be controlled, verified, traceable, and supported by evidence before it's deployed. One interesting question that comes up during these events or webinars is, can we trust the tools we're using to develop and verify the AI? And that's because 8800 doesn't say. There are many tools involved in developing an AI system. You have frameworks used to build and train the model, like PyTorch. There are data processing pipelines, libraries, simulation environments, test tools, and software used to evaluate the results. And any of those tools can potentially introduce an error or fail to detect one. So if we're going to use the output from those tools as part of our safety evidence, we need confidence that they are suitable for what we're asking them to do. That means understanding the tools, evaluating their potential impact on safety, and putting appropriate measures in place to detect or mitigate errors. What 8800 asks for is that you can justify your confidence in the tool for its intended use and provide the appropriate evidence. So one thing I want to emphasize is that AI models, again, don't operate alone in embedded safety critical systems. They are surrounded by conventional C and C++ software that monitor its behavior and implements many of the safeguards. If we're relying on these safeguards to protect us when the AI gets something wrong, we need confidence that that software itself is reliable. And that's where traditional verification techniques continue to play a critical role. So to operationalize this, we can start by shifting testing left. Static analysis allows us to identify defects and enforce coding standards such as MISRA, AUTOSAR, and CERT early in development. Then we have unit testing and code coverage. We can verify C and C++ functions according to the requirements. You can use a unit testing tool or framework like Parasoft's C++ test, or an open source framework such as Google Test. If you don't already know, we have extended our TÜV certificate to now include Google Test for use in safety critical software. And we have added code coverage, requirements traceability, compliance reporting, all on top of Google Test and other open source unit testing tools. So you actually get a complete C and C++ TÜV certified code verification package. And these tools can all be seamlessly integrated into your CI/CD pipeline. So static analysis, unit testing, code coverage, and then there's requirements traceability. Traceability is automated for you as well. Now, AI is also changing how we perform the verification itself. You can use AI to remediate static analysis violations, generate or improve unit tests, help close code coverage gaps, prioritize risk, and reduce the manual effort associated with verification and compliance. But there's an important statement to make. We're using AI to accelerate the engineering process, not to eliminate engineering judgment. The engineer still needs to remain responsible for reviewing the results and determining whether the evidence is correct or sufficient. So, in an interesting way, we've kind of come full circle. We're engineering safety for AI while also using AI to help us engineer safer software. That's a quick review of 8800, and there's other key points, but I covered the main ones. Let me see how to open this up for Q&A.